So this has to do with electronic properties of materials. And for many, many years, or for almost 100 years, physicists thought of electronic properties of materials as falling in two classes. There are really two types of materials according to their electronic properties. And those types are metals and insulators. So metals are things that conduct electricity. They're materials like copper or silver or aluminum. They are conductors. They also tend to be ductile. So there are other properties associated with metals. And insulators are materials like quartz or silicon dioxide, which is the basic component of glass, or diamond or Teflon. Those are things that don't conduct electricity. They tend to be also brittle materials. So one of the great triumphs in the 20th century of quantum mechanics was to understand why it is exactly that some materials are metals and some materials are insulators. Not totally obvious when you look at them. In fact, this problem is actually quite deep, and I'll give you an example of why, or just how deep it is. So the element tin, for example, can actually form two different crystal structures. So the atoms in tin can be arranged in one of two different ways. And we call them white tin and gray tin. Turns out white tin is the one you're most familiar with. If you melt tin and then cast an object, that form of tin is white tin. It's a metal, it's ductile. But it's not the only phase of tin. And in fact, if you take white tin and you cool it down to very low temperature, it'll spontaneously transform into gray tin, which is an insulator, and it's actually brittle. So this actually can have major consequences. So there's a story, it's possibly apocryphal, that when Napoleon's army marched into Russia, the buttons on the uniforms of the jackets were made of tin. And in the very, very cold Russian winter, that tin actually transformed from white tin to gray tin, became brittle and fell apart. And so the army was in tatters, and that's partially due to the fact that these buttons were made of tin and they transformed. So we want to understand why it is that the crystal structure actually determines or helps determine whether something is a metal or an insulator. So to understand that, we need to talk a little bit about what electrons are doing in the material. So what I'm going to talk about is the energy of an electron and its momentum. So momentum is a vector. It has a direction, and so it can either be forward or backwards. It could be positive or negative. And the energy that the electron gets is a scalar, and it's always positive. So more momentum means more energy, whether it's forward or backwards. And so we have a relationship between energy and momentum that looks something like this curve. So, okay, so now I need to tell you a little bit of quantum mechanics, just a little bit. The first thing that you need to know is that electrons are waves. So the fact that particles behave like waves is a fundamental part of quantum mechanics. The second thing that you need to know is that the wavelength of these electron waves depends on their momentum. So the larger the momentum, the faster the electrons go, the shorter the wavelength gets. So there's a wavelength of the electrons that depends on momentum. So why does that matter? Well, these electrons, we're talking about electrons that are inside a crystal, so they're inside a solid. And inside a crystal, there's a periodic arrangement of atoms. So there are actually special wavelengths. When the electron wavelength is equal to that atomic spacing, then it's in step with the atoms in the crystal. And in that case, there are actually two states the electron can be in. So the crests of the waves then can be right on top of the atoms, and the electrons like to be on top of the atoms, and so that lowers the energy. The electron's happy there. Or the crests of the waves can occur in the spaces in between the atoms, and that the electron's not as happy being in between the atoms, and that sort of raises the energy a bit. And so because the electron's in a crystal, and this crystal has these evenly spaced atoms, things happen when that wavelength or that momentum is such that the wavelength is equal to that crystal spacing. So what this does is it opens up these little gaps in this curve. And so now there are certain energies that are allowed for electrons in the crystal, and there are certain energies that are not allowed in these gaps. And so the picture that we developed is something like this. There are bands of allowed energies, and then there are gaps between those bands. And so this is the band theory of solids, and it helps explain a lot about the properties of solids. So the last thing we need to know to understand how this band theory determines the properties of the solids is that quantum mechanics tells us that for any given state of momentum and energy, there can only be one electron in that state. And so we've got a certain number of electrons to put into these bands, and what we do is we put them in at the lowest energy, and then they kind of fill things up to some energy where we've got all the electrons. And when we do that, there's two possible results. So we can have, once we've put all the electrons in, we can have a band that's half full, and those are our metals, or we can have a band that's completely full, and those are the insulators. So that explains why there's two different kinds of materials, and I can also try to give you a picture of why a half-full band would be a metal and a full band would be an insulator. So if I have this half-full bottle of water, this represents this half-full band. It's fairly easy to slosh the fluid around, the water in this bottle. And what I'm doing then, if these are the electrons in the band, you can imagine that it's fairly easy to create a state where there are more electrons over here in a state of positive momentum than electrons over here in a state with negative momentum. And so that means that those electrons are moving forward and they're carrying a current. So it's easy to create different kinds of states carrying different amounts of current by sloshing the electrons around or the fluid around. So that's the half-full band, which would be a metal. In a full band, no amount of sloshing creates any state that carries current because I can't make the positive momentum states any more populated than the negative momentum states, and so there's really no way to get current to flow here. So there's an energy gap in the way, and you have to give the electrons that extra energy to get over the gap. And that's very difficult to do, and so the insulator doesn't carry any current. It's interesting to think about this full band, because what this full band is it's electrons in different states of different energy and different momentum. And so the electrons are actually moving around. Some of them are moving to the right, some of them are moving to the left, but in net, there's no current flowing. And so even in an insulator, we think of electrons as actually moving around in some sense, but they're not carrying any net current. Okay,